Good morning, this is Professor Elliott, and in this short video lesson we'll be talking about the SCR, or known as the silicon controlled rectifier. So to start with, we're going to look at the four-layer diode, which is a precursor to the SCR. As we'll see, the construction internally in the operation is very similar, just a few little small changes, but let's start with this. So the illustration on the screen shows the internal construction of the four-layer diode, and we can see we have two terminals. This one's called the anode, and this was called the cathode, and you can see the internal structure there. In order to initiate conduction, and the four-layer diode and the SCR, which are part of the family known as the thyristors, it's used as an on-off switch, not as an amplifier. So if the switch is closed, current is flowing through it. If it's open, then we have no current. So it's just a simple solid-state electronic switching device. And in order to initiate conduction, we need to have that has to be positive with respect to the cathode, which would be negative. And when the anode is more positive than the cathode by a critical value called the breakover voltage, then the thyristor, the four-layer diode, will start conduction and behave very similar to a closed switch. So here we see internally what we have. Sorry about that. And we just simply have two complementary, so they're matched pairs. We have a PNP, and then we have an NPN transistor. So this is how they're connected. We have a current limiting resistor, and this would limit the current to a safe value of the four-layer diode. So when the device is conducting, again, notice the polarity anode to cathode. We've reached the forward breakover voltage, and current is then going to flow down through this transistor, right? This will be forward biased, right? This will then close a closed switch to provide base current down to this transistor, which will provide current collector to emitter for the lower transistor. So when it's conducting, it looks very similar to a closed switch. Remembering always that there's a forward voltage drop. It's typically not greater than 1 volt. So it's not exactly like a mechanical switch, and we talked about this last term, the transistors, but it's pretty close. So if the four-layer diode is not conducting, okay, so anode, cathode, look at the polarity, then behaves like an open switch, and the current here theoretically is going to be 0. Okay, but of course that because the device is not really a mechanical switch, right? Has leakage current through the junctions. So in reality, is going to be some very microamps of leakage current through there, but it's approximately behaves as an open switch. Okay, so this is the four-layer diode in a non-conducting state. So now let's add a gate lead. So the SCR, right, is simply the four-layer diode with the addition of a gate lead. Otherwise, internally, they are exactly the same thing. Okay, so here we have the four-layer diode, anode cathode, with our gate lead here. And then internally, then see how it's connected. Just the collector here and the base there are brought out to the gate lead, provide a gate pulse. A gate pulse, then we'll forward bias the base to emitter here. This transistor turns on and then allows current to be pulled like this all the way down. Okay, so that's when we have apply a positive gate pulse. And you go to the data sheet, there's a minimum width this has to be. This will be done in the microsecond range. And you take away the gate pulse, and this will stay latched because we have this feedback here, which will maintain the base current to keep the device into conduction. Okay, so again, just another drawing, just showing the internal construction again. Okay, if it's conducting, sorry, then we have current which is flowing anode to cathode like this, and of course the load current resistor R, whether this could be possibly a motor or a coil, like a heater coil or a light or something, something to limit the current and to do useful work. Okay, so the load current, the anode current, and the cathode current are all, of course, going to be the same thing. So again, so here we have a conducting SCR. We have a 24-volt battery. If the device is closed, ideally VAK is 0 volts. So this is the voltage anode to cathode, which is going to be over here, like there. Okay, we've already provided the gate pulse to initiate conduction. Okay, so this is ideally 0 volts, but practically this won't be 0 because it's a real device, but it's going to be typically much less than 1 volt. And but taking the ideal, if this is 24 and this is 0, Kirchhoff's law says this voltage across the load must be 24. Okay. Okay, device is non-conducting, and we have like an open switch here, essentially. So the load voltage is going to be 0. Okay, this voltage here is going to be 24. Practically, because of the small leakage current, this will be maybe 23.98 or 99, something a little less than 24, and this will be just a few millivolts. But anyway, the ideal is if that's 24, all the source voltage is developed across the SCR, leaving nothing for the load. Okay, so this is the characteristic curve. So the key points are the forward breakover voltage here. So this is really the same voltage we talked about with the 4-layer diode, that if you don't use the gate lead, and that's the whole advantage of using the SCRs, you can initiate conduction at any point in the cycle by providing a low voltage, low current gate pulse, so it's much more controllable and usable. But anyway, you could abandon the gate lead, use it as a 4-layer diode essentially, and allow the forward breakover voltage, which is typically 25 to 35 volts, depending on the device, somewhere in that range, to initiate conduction. The forward anode current (IF). Okay, it's arranged very similarly to a standard diode curve. IR is the reverse current down there. The forward voltage VAK, and that's going to be the voltage across the device while it's conducting. So this is the reverse blocking region. This is the avalanche region. We don't want to go there because we're going to just destroy the device. So anywhere up in here is the forward conducting region, and this is where the SCR is conducting as a closed switch. IH is the holding current. It's a datasheet value. Is the minimum current required to maintain, minimum anode current required forward conduction. And by the way, this is point here, this is for IG equals 0. So we're just using the breakover voltage. If we're using the applying a gate pulse, then it might trigger something like, somewhere earlier in the cycle like this, okay, or like this, depending on what we got. So anyway, there's the curve. Okay, so that's the end of the show. Hope you enjoyed it, and we'll catch you soon. Bye-bye.